Hey guys, and welcome to this video about Haskell. This video is basically here to help you if you consider taking a course in Haskell or in functional programming, like I did last semester at Trinity College Dublin. It was called an Introduction to Functional Programming, and we just covered like all the basic concepts of Haskell. So if you wonder what you can expect to get from that, what will stick to like your memory after exams and some weeks that have passed, this video will help you. Or if you're just in general curious what Haskell can be about, why it can be fascinating, and what I personally enjoyed about it. I'm not at all an expert, so this is just a broad overview giving you a few key concepts. And I want to say first that you should have some prerequisites in the beginning at least, like some intro to programming or to computation in general, maybe, where you learn some key concepts, like recursion, for example, because that will really help comparing Haskell to your previous knowledge. And that's what I'm going to do in this video as well. I will basically show you 5 key concepts that I learned over the course of the semester. Which is thinking recursively, declarative versus imperative programming languages, purity, lists, and at last also higher order functions. Okay, let's dive right in. Okay, the thing that stuck to me the most was definitely recursion, because you encountered probably in your first intro to in your first programming course, but you never really get an intuition for it, because most of the time you just use loops, for loops, while loops to go through stuff, and not recursion. And that really changes in Haskell, because there is no such thing as loops, as you just state things how they are. It's very mathematical in that sense, actually. And we're gonna have a look here in Notepad, where I just had my Haskell notes, and I'm just gonna give you some code examples. As you probably remember, and if you don't, no worries, recursion works like this. Let's take the factorial function as an example, and we say the factorial of 0 is 1. This is important to state because we want to have an edge case. Recursion normally goes down somehow, or like goes into further down the natural numbers or anything like that, and you want it to stop at some point. And you want to be sure that it gets to that point, because otherwise you get an infinite never-ending program. And then you want to say that the factorial of n is n times factorial of n. Let's keep it clear with the brackets, n minus 1. By the way, if you notice here that the argument is not surrounded by brackets, that is because that is the typical Haskell notation of arguments. So even if I added more arguments like this, it would just be separated by white spaces. And that has a reason in Haskell, but I don't have the time here to actually explain it, and I haven't grasped it fully, let's say. So this is recursion. And in Haskell, that's the only way to actually go through stuff multiple times, and you learn to perceive problems like this more often. Yeah, you're forced to, because that's the only way to go through this, to do stuff. And just as a quick reminder how that would work out, if you want to have the factorial of 2, you would say factorial of 2 is 2 times the factorial of 2 minus 1, that's just 1. Then we would want to know what the factorial of 1 is, and that is 1 times the factorial of 0, which is, per definition, as we can see here, that's our edge case. This is why it is important. This factorial of 0 is per definition 1. So we get that the factorial of 1 is 1, which we can give back to this one here, and we get that the factorial of 2 is 2. That's how recursion works. If you need more resources on that, I can link them in the description. And also link more detailed content in the description about the other key concepts I'm going to explain now. Yeah. So this is how you write Haskell programs. This is already a valid Haskell program you can see here. It just states what things are, and that also gets me to my next point, which is declarative versus imperative programming languages. Because that's a declarative worldview, kind of. You just state what a factorial of a number is. You don't explicitly tell the computer how to get there, or like the user or observer. On the other hand, Java is an imperative programming language, which gives you kind of a recipe. It says like, okay, you do this step 1, you do this step 2, this, then you go through a loop, then etc. You know Java programs, hopefully, or like any kind of imperative programs. Yeah. Haskell is also not object-oriented. There are no variables, like not in the sense of like global variables or variables that you can change over time. Like you can't say x equals 5, then you set x to y plus 5, then you set x to the result of the function, my function 1, 2, 3. You can't do that in Haskell. And there are also no such things as objects or classes. There's some similar concepts, but it's not like in Java. So that's declarative versus imperative thinking, by the way. Anyway. Which was my second key concept I took from Haskell. The third one was purity. And purity is simply put that if you have a function and you have some inputs, you should always get the same outputs without any side effects. And that means side effect means that there shouldn't happen something in the background you aren't aware of, and same input should also mean that it's mathematically the same. So if I have an input of 5, I should get the same result as if I have an input of 3 plus 2. Simply put. So let's give an example where we would have a side effect in a non-pure language like Java, where Haskell is pure. So let's say in Java we have a variable y. We assign this expression to the variable y. We have math function, and we have some arbitrary math function which does some mathematics and returns a number, and for example an integer. And and we do this 3 times actually. Always with the parameter x. So this should basically be the same as, let's put it like that, 3 times math function of x, right? That's basic arithmetic, from elementary school. And that's what I meant with same inputs. If you have that would be the same inputs, 3 times math function or math function plus math function plus math function. And let's now explain why we could have side effects here in Java. Let's imagine there's a global variable somewhere that counts how often math function is called. So every time it is called, we set this global variable to +1. So let's say we get into our program, our global counter variable has the value 0, and we, in the first case, call math function 3 times. So after we call it 3 times, it should have the value 3. While in the second case, you can imagine where this is going. In the second case, the counter global variable that counts how often math function is called is only set to 1 because it was called once. And this is a side effect. Now we have the same expression in Java, but we have some side effect. And we might not even realize this side effect as a programmer, which is kind of the tricky thing, and also a reason why people like Haskell or advocate Haskell, because of its purity. Its purity also helps if we... Oh, my battery's low. Okay. Purity is also great if you want to argue about why programs behave the way they behave, and if you want to prove stuff mathematically, because if it's pure, it's way easier to argue about, because you don't have any side effects, and Haskell is very close to how you would write down or define stuff mathematically. So it's really cool in that regard. And now we come to the next point, which is quite closely related to recursion in some way, and that is lists. So, lists. In Java you think of lists without any hierarchy. It's just an enumeration of stuff. Like, what am I just doing here? So, 1, 2, 3, etc. Just a list. In Haskell, however, there's a hierarchy, a recursive hierarchy actually. So back again to recursion, and it's this: every list consists of a head and a tail. Every list, except the empty list, by the way. The empty list is just the empty list. But every list that contains any element has a head and a tail, and the head is the first element, and the tail is the rest, which itself is a list. Which is recursively, right? Because you say a list is a list, list is an element in the list. And this list can also be empty. So if we had like easiest example, a list with exactly one element would be, oh god damn it, what am I doing right now? Would be the head 1, and then the tail, which would be the empty list. This would be the notation for it, right? We have here the head and here the tail, and that's the whole list. You would write it, would have a shortcut for that. Would be just one. Like in Haskell you can also type this, but this is the underlying structure, which you will access a lot, because if you loop, iterate through a list, you will do it with recursion, and you will do it by doing something to the head and then going to the tail and applying the function recursively. Let's maybe make it a bit more complex. It looks a bit weird. Like say we have the list 1, 2, 3. It would look like this: head is 1, and the tail is the rest, consisting of 2 as the head of the next list, and the rest, which would be 3 as the head, and now the empty list actually as the tail. So we have 3 tails here, like in 3 tails like inside each other, kind of. Our smallest tail is the empty list, our next tail is the empty list and 3, this one, together with the head 2, and our biggest tail is 2, 3, and the empty list together with the head 1. And Notepad helps us here by coloring the brackets red. So that's list. And the last concept I want to show is higher order functions, and that's also where the name or term functional programming comes from, as far as I know. And it simply means that a higher order function is a function that either takes a function as an input or returns a function, or of course also both. But it just means that you can handle around functions. You can put them there like normal variables. You can get them and give them to another function, and so on. Which is quite a funny concept. And yeah, just going to provide you with a quick example before we are finished. And that's the function map. And the function map takes a function as an input, like I just said. So map is a higher order function. Let's call that function f. And it also takes a list. Now you're going to learn some Haskell notation, because the notation for any list is this, or not for any, but for a list where you want to have the tail and the head and the tail. You will write it like that, so that you know that the head is called x and the tail is called xs. You could also call it something else, but that's just notation. And it works the following: map applies the function to the first element of the list, in this case the tail, and then recursively glues it together. This I forgot the name for it in English, but this double point thing glues the head and the tail together. So we glue the first element where the function was applied to together with the rest where we apply map recursively to the rest. So here we have a function called map that takes another function as an input, and this other function has to be unary, or like only taking one input, because it's applied to exactly one element. So for example, f could be add 1 to an element, to something, to a numerical value. And if we had, for example, as the list 1, 2, 3, and we would apply add 1 to every element of the list, we would get 2, 3, 4. That's a very straightforward, intuitive example, I hope, and it can get way more complicated, putting functions somewhere and doing stuff with it. But that's it. And if you want to understand recursion more in that case, you can just try that example with 1, 2, 3. You would see that you apply add 1 to the first element and glue it together with the rest of the list, because map returns a list, right? That's the return value of a list. That's the return value of map. It returns a list. So, and you would go back into map with add 1, the function add 1, and with the remaining list 2, 3, and then so it would go on. And maybe you might ask, what's the edge case here? And the edge case would be like the edge case in the sense of what I explained earlier with factorial, where the factorial of 0 is 1, and the map of f and the empty list is just the empty list. So if you get there, you just get the empty list. Okay, that's it with all the technical concepts. So to wrap it up, I can say I really enjoyed learning Haskell. It definitely gave me a different view on programming and how to think about it, how to think about it more recursively. And now I really see why recursion is elegant, why lots of people like it, or at least quite advanced programmers like it. And I also want to recommend a great tutorial for you guys. It's called learnyouahaskell.com, and it's written very informally with a great sense of humor, and yeah, it gives you a solid theoretical background but never asks for too much of you. So I can recommend it. You will find it in the descriptions. Thanks for watching. Hope you enjoy Haskell as well, and see you next time. Maybe with a video about Prolog.